Okay, so this is a tutorial. We're going to continue on with our discussion about average velocity, instantaneous velocity, and related to constant motion or non-constant motion. Also at the end of this, we're going to do a practice, or I want you to try a practice problem that looks at interpreting graphs. So we can, when we come into class, we can address any questions and then continue on from there. So as per the last lesson, we were talking about races and what races are all about, and I was trying to relate it to a situation between my wife and me. Okay, so we said that in general the point of race is to prove who or what is the fastest. Okay, and we all know this even if we don't think in those terms. So I said she can beat my butt in any race greater than 800, and I can beat her anything less than that. So whoever wins the race, we establish, has the greater average velocity or average speed. Really doesn't matter whether we're talking about speed or velocity here. And then as a sprinter, I can attain a greater speed at any given instant, even if it's a short time. And so we have to look at velocity in terms of instantaneous for other situations. Okay, so instantaneous velocity. When you're looking at the speedometer of your car, you're looking at your instantaneous velocity. How your car measures that is very different than how you would calculate how fast you're moving on average if you know the distance you went and the time it took. So the definitions for these, another way of looking at is that average speed is the rate of change of position for the entire distance or time interval in question, and instantaneous speed is the rate of change of position at a very specific time. Okay, so both have the equation delta x over delta t. Implicit in the definitions is that delta t for instantaneous is very, very short, and usually delta x will be short as well. So we can look at doing some simple calculations with one-dimensional models, and then I'm going to go back to the graph and talk about other situations. So let's take a look at a 1D motion once again, a little bit more complex than the one we referred to last page. So suppose we have a cat doing something or another, and we can take snapshots of where it is at various times. So from time 0 to time 6, and we can see where it is. Alright, so let's call this, instead of D, let's call that X in meters. Okay, it says the cat started from rest. We're going to cross that out. That's not true here. Okay, so you're asked to describe the motion for the entire interval based on what you see before you. So take a second or two and form an answer for that. Okay, so what I hope you noticed is that the spacing between each interval is not the same. So it's definitely not moving at a constant speed. It is moving because it's changing position. So our alternatives are it's slowing down or speeding up. Now I know we haven't formally talked about how you'd see that, but I think if you understand the idea of changing position with each time interval, you'll realize that we're covering less and less and less distance each time interval. So we can say that the cat is slowing down. That's about as much as we can say here, except that it's going forward still. Okay, so the reason I bring it up is now let's look at instantaneous and average speed in this context. So the average speed for the entire interval, if we use the idea of change in position over time, and we want the entire interval, our entire change in position, we went from 0 to 33. So if we still use V bar is delta x all over t, then we've got 33 minus 0 meters divided by 6 minus 0 seconds. So 33 divided by 6 is 5.5 meters per second. Okay, pretty straightforward. So in a sense, you're finding the slope of the entire event, even though you don't have a graph. Now we can ask, what's this cat's speed at the very beginning? Okay, so that's important. So we're looking at more or less an instant in time. The beginning implying from, let's say, the first time interval, which we really have information. I can't say how fast it's moving at this instant because I don't have enough information about changes, but I can look at how fast it's moving at the beginning from here to here. So we really don't care about what's going on hereafter, so we can still use v now, okay, as delta x over t, where t is a small interval. So our position change is from 8 to 0, or 0 to 8 I should say, and then the time interval is the first time interval, so 1 minus 0 seconds, and this is 8 meters per second. So that makes sense in the context of what we said before. We're slowing down. So if our average was 5.5 meters per second, it would make sense at the beginning we're going faster than the average, and indeed we are. And then we should expect the opposite at the very end. So at the very end, which is the last time interval here, we've gone from 30 to 33. So the change is the 33 minus 30. And again, it's 1 second, 6 minus 5. And so we have 3 divided by 1. 3 meters per second. Okay, so we have the average at the end, or excuse me, the instantaneous at the end is less than the beginning, good, and the average falls between these two extremes. And if we take the average of these instantaneouses, right, 8 at the beginning, 3 at the end, 8 plus 3 is 11 divided by 2, we see that we get to 5.5. And that kind of tells us something else about how we're slowing down. It's more subtle, but we could say we're slowing down at a steady rate. The steady part we see because the average of our instantaneous at the beginning and end is equal to the average. And that doesn't always have to be the case. So we'll look at that idea of a steady rate of slowing down a little bit later in our learning of this. Okay, so key point. When speed is changing, we've made this before, average speed for an entire event is very different than instantaneous speed. At any given point. Okay, we could ask ourselves, is there any point in this interval where the instantaneous speed equals the average speed? And we would just basically have to look for an interval where we cover roughly 5 meters. So from 3 to 4, we go from 21 to 26. So during the interval, we're pretty close, or maybe between here and here, we're pretty close to going at the average. Okay, but we'll look at those aspects another time. Alright, so that's really it for the introduction. So what I'd like you to do is we have a practice page. I'd like you to try this on your own. Okay, we have a position time graph. I want you to basically fill out the chart, put a check, a yes or no for moving, constant speed, put a check. We didn't formally talk about going faster or slower. I want you to give that a try. I think you can figure that out. Remember, you're looking at the steepness of the slope, and if the steepness is changing, you can infer whether it's getting less or greater and determine if it's going faster or slower. And then do direction. And then there's a few questions below to ask. Okay, so I'm going to just delay for about 10 or 15 seconds. You should pause it, but then I'm going to put on a page that shows the answers to this so you get some feedback. Okay, so go ahead and start, but I would pause it right now. Okay, so let me reveal the answers. It's assumed you've taken 5 minutes or so to look at the answers. Okay, so here is the page. Alright, unfortunately I can't fit the graph and the answers on in the same screen. So let me just display the answers and you'll have the graph in front of you. Okay, so it should have been pretty clear whether you had motion. Should have been pretty clear that A and F were constant speed and E was not moving. Whether you got faster, slower, correct or not, we'll talk about in class. It was forward the whole time except at the end. In terms of averages, we just found the slopes of the various segments, total change divided by total time. For each of these, this had a negative velocity. An important point, the instantaneous and average are the same when you're on a segment where the speed is constant. Easy mistake to make on this one is to say B is faster, because if you do the total distance divided by total time, you'll get a bigger value than if you do it for F. But when you do total distance divided by total time, you're getting average speed, not instantaneous, which is what this is asking for. average velocity of the whole trip, our displacement was 0, so in essence we didn't go anywhere. And then the speed tells us really how quickly we were moving the entire time. Okay, so that sums up the ideas of motion graphs. We'll do practice in class next time we meet.